At first sight, it sounds crazy and radical. I must say it was very surprising to us that this solution works.
Standard physics describes black holes with these paradoxical interiors, these regions that end space-time. They have infinite curvature, information is lost. Now, Professor Neil Turok is upending this view with black mirrors, a theory which incorporates something called CPT symmetry and analytic continuation, all of which are explained in the episode itself. It makes black holes two-sided structures without interiors. The event horizon becomes a surface where matter meets its antimatter counterpart from a mirror universe and annihilates.
We literally replicated Hawking's black hole calculation and we were very surprised we could do it at all.
It's a pursuit yielding a finite theory.
A theory without no infinities. So that's very exciting. It's brand new.
Potentially explaining particle generations.
We cancelled the vacuum anomalies. We explained why there are 3 generations of elementary particles. It is, as far as I know, the simplest explanation anyone has ever given.
And bypassing trappings like extra dimensions and cosmic inflation.
We don't need to keep inventing new particles, new dimensions, multiverses. I think the whole field sort of went haywire. We shouldn't overcomplicate physics.
While we touch on abstruse mechanics like non-invertible matrices and null energy conditions, don't worry, Neil is a master explicator, and today's podcast requires no prior physics background. We even discuss Interstellar's depiction and why he deems ergodicity arguments for cosmic uniformity to be absolutely wrong. You recently released a controversial paper on black holes and how they're more akin to black mirrors. Explain the primary idea behind this result and why it's caused such a stir among a subset of physicists.
What we are explaining is a mathematical solution to Einstein's equations, which describes black holes rather differently than the conventionally accepted solution to Einstein equations. So it was motivated by our work in cosmology, where we noticed that the Big Bang singularity is actually not all that singular. And we used a technique called analytic continuation, which is a mathematical method related to complex numbers, a very powerful, very beautiful method, which often works in physics. And we used that method to traverse the Big Bang singularity and find a mirror universe on the other side. So one of my PhD students was bold enough to say, why not try this for black holes? And I myself hadn't attempted it because I thought black holes are a lot more complicated. But sure enough, he was able to get the same method to work for a black hole. And strangely enough, it gave a new and alternative interpretation of black holes themselves. So, in essence, the point is that the black hole horizon is a rather special surface in space-time. You should think about it as a two-dimensional surface enclosing the black hole. But if somebody inside emits a signal, we will never, ever receive it. And so you may wonder, is the inside real if we can never receive a signal from the inside? Now, the conventional interpretation is that it is real. And that leads to all kinds of paradoxes. If something falls into a black hole, the information it carries is lost and can never be received outside. And the paradox gets even worse if the black hole evaporates quantum mechanically, as
Right.
Stephen Hawking described, which is widely accepted that black holes will evaporate because this information is then lost forever. And that's incompatible with quantum mechanics. Quantum mechanics doesn't allow you to destroy information. So, and there are other puzzles about black holes. You see, if we watch somebody falling into a black hole, we as outside observers would never actually see them falling through the horizon. What we'd see is that their time would effectively slow down, and anything they were doing, anything they were using like clocks would just slow down and freeze. And the ultimate picture we would have of them is that they're just frozen on the horizon. And so again, people have wondered, if what happens inside the black hole is never actually observable, is it really true that the interior of a black hole even exists? So we applied this method of analytic continuation to the metric of a black hole. We actually did it for ourselves, or my student did it for himself. But later we discovered that Einstein himself had used the same method before the conventional description of a black hole was discovered by Martin Kruskal. Martin Kruskal discovered how to describe the transition across the horizon in a, let's say, kosher mathematical way, I think around 1960. But even before that, Einstein was puzzled by the black hole horizon. And Einstein and Rosen, the same people, Einstein, Podolsky, Rosen, the famous EPR paradox in quantum mechanics, the same Rosen with Einstein, solved the equations for a black hole in a different way. And basically, they use this technique to transition through the horizon. And they discovered what is called the Einstein-Rosen bridge. And this connects two exteriors of the black hole, which are really distinct universes. And as you go through as you follow the solution to the horizon and beyond, you emerge in the other side of the black hole. And in fact, this is absolutely analogous to what happens in our description of cosmology. We go back to the Big Bang and we just follow it through and we come out on the other side and there's another Big Bang there. And it turns out that all known solutions of GR have this form. All known black hole solutions and all cosmological solutions which begin with radiation domination, as ours seems to, they all have this property of the two-sided character. So, but what surprised us is that when we found we emerge on the other side without even noticing the black hole interior. Okay. So mathematically, effectively, you hit the horizon surface on one side and you come out on the horizon surface on the other side into the other universe without seeing anything in between. So there is no black hole interior in this solution. Now, that seems strange. Something must go wrong because we've managed to avoid, the singularity. Because in the middle of a black hole, inside the black hole, there's this curvature singularity, which is where the Einstein equations break down. And, if you fall into a black hole, you're going to hit the curvature singularity. There's nothing you can do, and you'll be sort of crushed and stretched infinitely. So the standard description has this severe problem that inside the black hole, the equations fail. That doesn't happen in our case, but something else does fail. It turns out that in the usual picture of general relativity, you have this space-time metric, which you use to measure distances. And in the normal approach to general relativity, that's a matrix. This method is a 4x4 matrix. And one of the axioms is that it must be invertible. You must be able to write down the metric and its matrix inverse. It turns out that in this coordinate system we are using, and which Einstein used before us, Einstein and Rosen used before us, the metric fails to be invertible exactly on the horizon. So it's completely analytic, meaning it solves the field equations, but this one axiom breaks down on the horizon. So we would say we have a type of singularity. It's in the conventional sense of GR. You can't only use conventional GR to make sense of this, but it's much milder than the singularity you would otherwise have if you took the inside seriously. So in other words, we found a way of avoiding all curvature singularities in black holes, which involves accepting another kind of singularity, which is this. Essentially what happens is the metric is not invertible on this surface. Now, Is that a catastrophe that the metric is not invertible? No, by no means. There's nothing, God-given that says that the geometrical description, you see, essentially the idea that the metric is invertible can be phrased much simpler by saying that locally, in space-time, if I use a magnifying glass, and I zoom in as much as I can, then locally the space-time just looks like flat Minkowski space. There's no impact of gravity at all on short distances. That's the usual, the way. And if you say that, then when you zoom in on a given point in space-time, you can always use the Minkowski metric and just forget about gravity. And the Minkowski metric is invertible. So that's the usual justification. So we are saying something special does happen on the horizon, but it's not that bad. Okay. It needs a physical interpretation. What special is happening? Now, the special thing that's happening is to do with CPT symmetry.
Great.
So CPT symmetry is charge conjugation, parity, and time reversal, which basically means that you take the conventional description of it is you take the coordinates in space-time, which we think about as numbers. There's the time coordinate and 3 space coordinates, and you replace them with minus themselves. Now, probably the nicest way to think about this is if, in effect, you are rotating space into time. Okay, so if I think of time going up and space going sideways, you do a rotation by 180 degrees, so time goes down and space goes in the other direction. So that is what do we call a PT transformation? It's parity, reversing space, and T, time reversal, reversing time. Now, in special relativity, you're not allowed to rotate space into time. Okay, we're allowed to rotate space into space because we see that the world is pretty much invariant under rotations in space, but you can't rotate space into time. Why? Because in special relativity, you're only allowed to boost, meaning you can travel faster, and that has the effect of squishing space and stretching time, but you can't actually rotate them into each other. Now, again, this comes into the mathematics of complex numbers. So it turns out that in particle physics, when you calculate scattering of particles or any event involving ingoing and outgoing particles, you are allowed to rotate space into time, and that's a exact symmetry. So one of the most famous, expositors of quantum field theory is Sidney Coleman. And he has this beautiful book. His lectures at Harvard are sort of a classic, and his students wrote them all up. And they're the best place to learn about CPT, by the way. And Sidney says, look, if we discover in an experiment that charge conjugation is violated, when you change a particle into an antiparticle, you discover that physics changes. That's no big catastrophe. If parity is violated, inverting space is not an exact symmetry, that's not a catastrophe. And same for time reversal. The laws of physics we know do actually violate time reversal, space inversion, and charge. Each of them is violated separately. But, he says, if CPT is violated, that is a complete calamity. We would have to start all of physics again. Okay? So CPT is very profound. Now, it changes particles into antiparticles. And the nicest way to picture this geometrically was realized by a guy called Stuckelberg in 1941. And so he was a genius in Austria who was not sufficiently recognized in his lifetime. But he realized that if you think of space and time, so time goes up, space goes sideways, and now think of a particle. What's a particle in space-time? So a particle is what we call a world line. So this particle is a curve, or every particle follows a curve through space-time. So if I slice the space-time in the time direction, I'll see this point moving along in space on different slices, as the slices proceed.
I want to take a moment to thank today's sponsor, Huel, specifically their Black Edition ready to drink. So if you're like me, you juggle interviews or researching or work or editing, whatever else life throws at you, then you've probably had days where you just forget to eat. Or you eat something quickly and then you regret it a couple hours later. That's where Huel has been extremely useful to myself. It's basically fuel. It's a full, nutritionally complete meal in a single bottle. 35 grams of protein, 27 essential vitamins and minerals, and it's low in sugar. I found it especially helpful on recording days, so I don't have to think about prepping for food or stepping away to cook. I can just grab something in between conversations and keep going. It's convenient, it's consistent, it doesn't throw off my rhythm. You may know me, I go with the chocolate flavor. It's simple and it doesn't taste artificial. That's extremely important to me. I was skeptical at first, but it's good enough that I keep coming back to it, especially after the gym. Hey, by the way, if it's good enough for Idris Elba, it's good enough for me. New customers visit Huel.com/theories of everything today and use my code theories of everything to get 15% off your first order plus a free gift. That's Huel, HUEL.com/theories of everything, all one word. Thanks again to Huel for supporting the show. Become a Huel again by visiting the link in the description.
I'll see this point moving along in space on different slices, as the slices proceed. So Stuckelberg said, okay, that's the picture of a particle in relativity. And in classical general relativity, it can't go faster than light. And that always means that this line going up in time, if the particle is stationary, the line just goes vertical. But if the particle's moving, it goes at an angle to the time axis, because moving along in space. It's not allowed to go faster than light, so it can't. The slope can never be bigger than 45 degrees from the vertical. And so Stuckelberg said, wait a second, in quantum mechanics, we have processes called quantum tunneling, and they allow things which are impossible classically, like particles going through walls, but they're perfectly possible in quantum mechanics. He said, even though classically a particle can't go faster than light, quantum mechanically, surely it's not disallowed. So he said, what happens if I have a particle which is traveling forwards in time, okay, and then it gets faster and faster, and its world line tips over, and it ends up going backwards in time? And he said, that's got to be allowed by quantum mechanics. And he interpreted. He said, you see, when it's going forwards and we do our time slices, we will see a single particle going up that where the line intersects the plane. But when it comes back, we see another particle, except it's going backwards in time. And that's an antiparticle. And Stuckelberg realized that quantum mechanics and relativity inevitably predicts that for every particle, there is an antiparticle. And the interpretation is that an antiparticle is just a particle that happens to be going backwards in time.
Yes, many people attribute this to Feynman.
Yeah, that's not right. Feynman got the idea from Stuckelberg.
All right.
And Stuckelberg left so-called fundamental physics and worked on chemistry, mainly because his work wasn't appreciated enough. But as time goes on, you will find him mentioned more and more and more often. He had incredibly deep insights into what we now call quantum field theory, actually long before Feynman.
Wouldn't that also show a particle disappear? Oh, no, but that's right. If there was a particle, antiparticle, right.
Yes, so the interpretation of this funny curve up and down is that our interpretation, our picture of it as time proceeds is we see a particle and antiparticle, and they come along and annihilate. And we see that in laboratories all the time. And likewise, you can have a particle coming in from future time and turning around and going back up again. And that's pair creation in an electric field. If you switch a strong electric field on, then it literally pulls an electron out of the vacuum in the direction opposite to the electric field, and it pulls a positron, a positively charged electron, or the electron's antiparticle. It also pulls that out, and the two together go flying apart. And Stuckelberg said, this is inevitable. You can have this process. Now, in fact, the particles annihilating and the particles being created, the pairs annihilating or being created, those are CPT conjugate processes. If I just turn the picture upside down, which is the CPT transformation, the one is exactly the other.
Yes.
So the rates of them have to be identical. And that's the CPT theorem. So our picture of the Big Bang is, in fact, completely the same mathematically as a particle-antiparticle pair being created. We have these two sides of the Big Bang, something, our universe coming out of the Big Bang, and then on the other side, the CPT image or anti-universe. From our perspective, it's going into the Big Bang with a sort of reverse direction of time. But from its own perspective, it's just the same as ours. And so we see this happening in physics, the consequences of CPT symmetry happening in physics we absolutely know and trust. And all we have done is generalize the same mathematical principles to cosmology and now to black holes. Now, to come back to the black hole, when you fall into the horizon and you hit this special surface, what's going to happen? Well, what happens is very dramatic. As you fall in from this side, the other side is part of the anti-universe. And so there is antimatter. There's an antimatter version of you falling into the other side at the same time. And both of you will hit the horizon at once. And what will happen is the particles you are made of and the antiparticles the other the other version of you is made of will annihilate into radiation. And that will travel up the horizon and eventually escape when the black hole evaporates. So it is a complete picture, not only of formation of what black holes are, but of how they can evaporate and where the matter that forms the black hole ends up, which is it just annihilates into radiation and runs off to infinity. Now, I have to say that only the first part of the story, the stationary black holes, so this would be Schwarzschild, which is not charged or rotating, or charged black holes, exactly the same thing works, or even rotating charged black holes, which are the most general case. We've shown that mathematically they all have exactly the same property. But what we have not shown is that in the time-dependent black hole case, a black hole actually forming by a collapsing star, and then evaporating, that's a much harder problem to describe. And so we're working on this, and basically this requires new approaches to solving the time-dependent Einstein equations, which still need to be developed.
I see.
So this is still in a work in progress, but it's very exciting because potentially there would even be signals of this matter-antimatter annihilation on the horizon.
So your innovation and your collaborators as well wasn't just analytically extending.
Right.
Okay, because that's been done since the 60s, as you mentioned.
Yeah, no, but the funny thing is that this particular way of analytically extended preceded the work in the 60s. As I said, Einstein and Rosen used it. But they, of course, only did Schwarzschild, the simplest solution that was known then. What we've done is use actually the same analytic extension, but we've applied it to all possible black holes, and we find it still works. And so, I think the fact that there was an alternative was not noticed by people in general relativity because they were insisting that the metric has to locally look like Minkowski space-time at every point in space-time. And that does not happen on the horizon. On the horizon, you have this funny... Technically, you say that two of the eigenvalues switch. That's what happens on the horizon. The time-like one becomes space-like, and the space-like one becomes time-like. So they both go to zero on the horizon. So something, let's say, different than normal GR, general relativity, does happen on the horizon mathematically. But to us, it seems like this is easily the most minimal resolution of all the puzzles associated with black holes. I mean, our whole philosophy is that we shouldn't overcomplicate physics. We need to always look for the simplest, most minimal resolution of the most profound puzzles. So, what was the Big Bang? We claim we can understand that by this process of analytic continuation. And there's some new developments on that front too. When dealing with black holes, we would say that the conventional description has these pathologies, that you lose information, that you have a curvature singularity, which is just unremovable. I mean, it means the theory fails irredeemably. Finally, actually, the conventional description is inconsistent with CPT. It's just inconsistent. And actually, Stephen Hawking, the last paper he ever wrote on black holes, was called something like The Black Hole Information Loss Problem and Weather. Okay. It was a funny paper. It was about, he was trying to explain that if black holes evaporate, the information gets scrambled. And it's more like the weather. We can't predict the weather tomorrow, but that doesn't mean we don't believe the equations. But during this paper, he explained that one of the basic paradoxes with black holes is they seem the usual description seems to be incompatible with thermal equilibrium. So what is thermal equilibrium? Thermal equilibrium is where you have stuff, let's say in a box, and it's hot. And so if it's molecules, they're flying around at high speed and interacting with each other. And there will be radiation that's bouncing off the walls of the box. This is a very generic physical situation, that you have hot stuff in a box and it's fluctuating into all kinds of configurations. So imagine you put a black hole in this box. Well, CPT symmetry demands that for every process forming a structure, like forming a black hole, you're inevitably going to form black holes out of, matter happening to fall in towards itself. So every process in which you form something, there must be an exactly equal process in which it unforms. That's what CPT symmetry says. Whatever comes in at whatever rate, there must be an exactly mirror image process where stuff comes out and unforms that structure. Now, in the usual description of black holes, that's impossible because stuff falls in and forms a black hole, and that's the end of the story. I mean, you can't unform the black hole. So he said the conventional picture of a black hole is incompatible with CPT because we don't have white holes. There's a black hole where things only fall in, but there is also a white hole solution where things come out.
Mm-hmm.
And the problem with the usual description is that we ignore the white holes, and we only include the black holes in our description of thermal equilibrium. And Hawking said that just doesn't make sense. So our black mirrors, we believe, are perfectly compatible with CPT. That's how we construct them. And therefore, they're perfectly compatible with thermal equilibrium. So they seem to have a number of advantages. But as I mentioned, a lot remains to be done to understand when such a black mirror actually forms. What is seen from the outside as it settles down, or in particular, if two black mirrors interact. It's a very tough problem. And there's such exciting progress, in the last 20 years, because now we can literally see black holes merging, and as they spin around each other, they emit gravitational waves, and we see them actually merge into a bigger black hole. So all of this stuff is now possible to watch happening. In the next few years, there will be literally movies of black holes merging, because the gas which surrounds them is like a tracer. And so we can see the gas with radio telescopes. And so with powerful enough radio telescopes, we can actually see all of this amazing physics happening. So that problem of understanding exactly how two black holes merge was only really solved about 20 years ago, using powerful computational techniques and supercomputers. You can put Einstein's equation on a computer and see what it predicts. But that's the prediction from the conventional picture, and includes the black hole interior. In our prediction, you basically need what is called different boundary conditions on the horizon than the ones people would normally use, and those will change the evolution of the black holes. And so that's going to take some time to sort out. It's a harder problem to solve than the conventional approach, because in a certain sense, we are putting in a boundary condition in the future as well as the past. You see? You'll notice that when I turn space-time upside down, the future becomes the past, right? And that's one of the appeals of our cosmology picture, is that we claim that the arrow of time emerges in this picture, because on the two sides of the Big Bang, you've got time going in different directions. So time goes forward out of the bang on both sides.
Yes.
And somebody inside the universe, would see only one of those two arrows. And so we claim that the arrow of time emerges from a Big Bang within this CPT symmetry picture, and doesn't have to be put in from the outside. In conventional approaches to physics, the arrow of time is just put in at the beginning with no explanation, even though the laws of physics don't violate CPT, which includes time reversal. People just assume that the state of the universe somehow does violate CPT. Now, when it comes to solving these two merging black holes, usually people would specify the configuration of the black holes at one time, and then just run the equations forward to see what happens. But in a CPT symmetric picture, it's a little more involved, because what you have to do is impose conditions, not just in the past, but in the future.
Now, why wouldn't it be that by imposing conditions on the past, it automatically imposes conditions on the future if they're symmetric?
Good point. That would be true classically. Okay. But in quantum mechanics, quantum mechanics is very different than classical mechanics in the way it treats the past and the future. In classical mechanics, the world is a machine. You just specify the configuration, like the particle positions and momenta, at one time, and just run it forward. In classical mechanics, you cannot specify the complete state of the system at two times. Not allowed to do that. I mean, if I tell you what the positions and velocities are now, you can't tell me, oh no, they would, I'm going to freely specify them at some later time. It's inconsistent, because it won't agree with the evolution of the initial condition.
Mm-hmm.
But in quantum mechanics, this is not true. In quantum mechanics, you are free to specify the wave function at two times. And so I can tell you what the wave function is at one time. You see, it's only a function of the coordinates.
Right.
And I'm not allowed to tell you the velocities if I told you the wave function of the coordinates. So if I tell you the coordinates. So you can either specify the wave function of the coordinates or the wave function of the momenta. You can't do both. But the upside of that is I can tell you what the wave function is at one time, arbitrarily, and I can tell you what it is at a different time, arbitrarily, and then I can predict what happens in between. And this is a point made by Yakir Aharonov, who's probably the deepest thinker on quantum foundations today. And in fact, all he does is think about paradoxes and puzzles and thought experiments, and he does it better than anyone else. And his point is that in quantum mechanics, it's very natural to have two times. Our point is that allows you to impose CPT symmetry on the universe, because you say, I take my initial wave function and my final wave function, and CPT symmetry asserts that they are identical. And then I just figure out what happens in between, and we live in between, and we can then predict everything that happens in between. So in the case of the black hole, we would tell somebody who's going to do a simulation of black holes merging that you should specify the initial condition, let's say, of the matter falling in, but incompletely, okay? You can only tell me the momenta of the particles coming in, not their positions, or vice versa. And then you should, if in the CPT symmetric picture, the outgoing state has to be the image of the incoming one. And those two, when they're adjusted, will give this special behavior on the horizon, which is the same as you get in the stationary black holes, where everything is, I say, analytic on the horizon. So basically, what seems to be required to predict the fate of a black hole is to say something about the future as well as the past. Now that, at first sight, it sounds crazy and radical and so on, which it is. But in this two-sided cosmology, it's absolutely natural. Because in the two-sided cosmology, we have the future coming out of the Big Bang, the future universe, the past universe coming out in the opposite direction. Now, really, these two are mirror images of each other, because the final condition is the same by CPT symmetry, or it's related by CPT. So the one is literally the mirror image of the other. So what I can do is fold the lower universe. Think about it as a sort of cone coming out of the Big Bang. So fold it up so that it doubles the upper cone.
Yes.
Now what I have is what we call a two-sheeted universe. We've got and it's just like the particle-antiparticle pair. Imagine if you really put those two things on top of each other. This double-sided universe is like the universe-anti-universe pair, and they're parallel to, you can think of them as being parallel to each other. You see, the picture is very beautiful. It says that the future universe you should think about as a sheet, as one of two sheets. And there's, if you like, the past universe is the other sheet. Now, what goes on when you make a black hole? Well, literally, you cut a triangle out of the future sheet, and the same thing happens on the past sheet, and but those two cut-out triangles are put on top of each other like this, and there's nothing in between. There's just a seam where they join, where the two sheets join. So the black hole horizon is the seam. There's nothing inside the black hole. There's a hole in this double-sided universe. And then when the black hole evaporates, the whole thing re-glues, and the black hole goes away, and we're left with two sheets again. So the black hole, the formation of black hole is literally just the sticking together of the past and the future universe, in which the section that's stuck together is just eliminated. It doesn't exist. It's literally a hole in this double-sheeted picture. But all you have on the sides of the hole are, a seam.
Okay, I have some technical questions, but people who are watching, before I get to them, they may be wondering what happens to me as I fall toward the black hole.
Yes.
So what happens to me in the traditional picture prior to this paper?
Right.
And then what happens in your view, or in you and your collaborators' view?
Brilliant. Yes, exactly. So the traditional picture is that you would experience nothing special at all as you cross the horizon. You're sitting in your spaceship, you see, the matter of when you cross the horizon is there are actually different definitions of when you cross the horizon, because the horizon is a somewhat subjective um, notion, in the sense that if I'm trying to communicate from my spaceship to another spaceship that's, let's say, further out from the black hole, depending on exactly where that spaceship is, I may or may not be able to send signals. So when I cross the horizon, the usual definition of what's called the event horizon
Right.
is that when I cross the surface, I cannot communicate to someone at infinity, at infinitely far away from the black hole. No signal I send will ever reach infinity. But if someone's nearer, you may be able to communicate with them. And so there's something called the event horizon. There's something called the apparent horizon. This is a surface which Roger Penrose defined in his proof that black hole formation is inevitable. And his definition was much more physical. It was that if you imagine sending out light rays in this the space-time where the black hole is forming, there will be some of those shells of light rays will start reconverging. And when they reconverge, they can never diverge again. So basically, when the outgoing light rays start to converge, you can call that when the black hole is formed locally. And so that's called the apparent horizon. So so there's still this ambiguity about exactly where the horizon would be. Our best guess so in the conventional picture, nothing happens at all. You just fall across the horizon. Okay, some of your signals
Both horizons, doesn't matter if it's apparent or if it's an event?
doesn't matter. In the standard picture, it doesn't matter at all, because locally, you have no idea whether your signals are ever going to reach somebody. It's not something that concerns you at all. You might send a signal and nobody ever receives it, but so what? You don't experience anything in the standard picture. You just fall across the horizon and nothing happens to you at all. What happens next is very dramatic, because you then inevitably fall into the singularity and get crushed. So that's the standard picture, where nothing exceptional happens at the horizon, at either horizon at all. The horizons, by definition, are just, where light either fails to make it off to infinity, or the outgoing light rays start to reconverge. And in fact, that doesn't really affect you at all either, because it's a very global property. It's not something you could measure locally.
Okay, so when does this crushing occur that people see in sci-fi movies? And where's the hypercube from Interstellar?
Oh, it's at the singularity. Okay, so in Interstellar, the assumption was that they went into the black hole, and then something very spectacular happens at the singularity itself. Now, the truth is that no one has a clue how to make sense of a curvature singularity in general relativity. What happens is that space shrinks in one direction, and blows up in orthogonal directions. So typically it shrinks in one and blows up in two, or shrinks in two and blows up in one. And that's just sort of a catastrophic failure of the theory. The whole picture of space-time gets stretched and crushed alternately. In fact, there's something that happens there called Mixmaster chaos. And the Mixmaster was a machine in the 1960s, which is a food blender. Okay, so some company, I'm not sure which, maybe it was General Electric, made Mixmasters. And so this phenomenon of this space-time in which things get crushed and stretched and crossed and stretched alternately is called mixmaster behavior. So that is the classical expectation. And in Interstellar, that doesn't make any sense. Everything goes haywire. So in Interstellar, they replaced this by somehow time travel, right? And the ability to communicate, let's say, across time. But nobody really has, I would say, a good physics idea for how to make sense of what happens to you. There are notable attempts by people who study holography, and they have a much more radical picture than ours, which is that there are wormholes. I guess it's a little bit like Interstellar. There are wormholes which connect the interior of different black holes and share information across these two black holes. But to be honest, I've never been able to make sense of that picture. It's far more radical than ours.
Okay, so in the traditional picture, you pass these so-called horizons. You don't notice anything as you're passing through. And then eventually you get squeezed into a tube, and then you reach what is called the singularity, the curvature singularity, because just like there are different forms of horizons, there are different types of singularities.
Curvature singularity, that's right.
So you meet that, and then no one knows what occurs once you meet that. Okay, that's the traditional approach since the 20s, 30s?
That's the traditional approach. I would say no, it became accepted after Kruskal analyzed the Schwarzschild metric, which is the metric of a non-rotating, non-charged black hole, the simplest black hole. Kruskal analyzed it and realized that there was a way to analytically continue across the horizon, which left the space-time locally Minkowski everywhere, except at the singularity. So, yeah, the conventional picture was only really began to be accepted in the 60s.
Okay,
but since then it's been. I mean, all the general relativity community has essentially bought the standard picture.
Okay, and now you come in. So the person listening is wondering, they are falling toward a black hole. What do they see as they're going toward it, and what occurs as they move past the horizon, if they can even move past it?
Yes. Good. So essentially nothing happens in this picture until you encounter the special surface. And then something extremely dramatic happens. And this is well before anything would happen in the standard picture. What happens is that you encounter antimatter. You encounter an anti-version of your spaceship containing an anti-version of you.
Of yourself.
Yes. And the two spaceships would meet, annihilate into radiation, which would then fly up the horizon and off to infinity. So it's extremely dramatic. It could not be more different than the standard picture.
Now, would you even see that other person? Well, let's say there is
No, you can't. You would never. You don't have a chance because the way light travels in the space-time forbids you from actually seeing any signal from the other side until you hit the horizon. The horizon is the first surface at which I could actually see something coming from the other side. I cannot see it before I hit the horizon.
Yeah, in your paper, you joined two boundaries, one of sigma plus 0 and one of sigma minus 0.
Exactly. So sigma equals 0 is where the two join, and neither side knows anything about the existence of the other side until you hit that special surface. So, it's a very different picture. By the way, some ideas which in a certain way anticipated what we did also became popular briefly in the string theory community in the, I guess, 2020s, 2000s, which was called the firewall. People argued, and this was Joe Polchinski and Don Maroff and others, they argued that because black hole formation violated quantum mechanics so badly in the conventional picture, there had to be a different resolution. So they argued there must be a firewall. There must be something which prevents you from going into the interior. And, there was a lot of these are very smart people, and there was a lot of debate about it, but I think it was inconclusive. So our picture, I think, is a better I would claim, a better motivated mathematical description than a firewall. But, something very dramatic is going to happen when you hit the horizon. And it's important to realize that process is quantum. As you hit the horizon, the process of pair annihilation, as I described at the beginning, it cannot happen quantum mechanically. It's just not, classically, it's not allowed.
Mm-hmm.
It depends on the particles going faster than light for a brief quantum moment. This curve turns around. That's pair annihilation. And what we're claiming is that is exactly the process which saves the black hole in the sense of making it compatible with quantum mechanics, is that the particles come in from one side, the antiparticles from the other side, they annihilate and sail off as radiation, and there is no interior to the black hole.
So I imagine that you checked other invariants to make sure there's no other form of curvature like the Kretschmann scalar.
Exactly. No, everything is completely regular. All curvature invariants are regular at the horizon. It's nothing new, but all we're saying is actually we found an analytic solution of the Einstein equations which extends, as I said, up to the horizon of the first exterior and continues onto the horizon of the second exterior without including any interior. I mean, I must say it was very surprising to us that this solution works. We were expecting to find something on the horizon, like a kink in the geometry which forced you to have some kind of stress energy source. This is typically what happens in general relativity. If you try to make a spaceship, for example, which goes faster than light or, violates any of the classic principles, you generally find you have to introduce weird forms of matter which kind of allow this behavior. What we found is we didn't have to introduce anything. This is just naturally there in the Einstein Einstein theory.
So you don't introduce any odd forms of matter, but there is an odd metric. Is that what psychologically prevented people from coming up with this solution?
Yes.
Because CPT symmetry is known and analytical continuation is known. Combining them has this, what is it, an eigenvalue degeneration on the surface?
Exactly. Yes, it's a swapping over of eigenvalues. So in the spacetime metric, one of the eigenvalues is, let's say, negative, and 3 are positive. Okay, it's a conventional choice whether you make 1 positive and 3 negative, or 1 negative and 3 positive. But let's stick with 1 negative and 3 positive.
Sure.
So what happens when you hit the horizon? The horizon is a 2-sphere. And it's completely regular. So that has 2 positive eigenvalues, and they're all fine. There's nothing weird in those 2 dimensions. They're perfectly regular geometry. There are 2 dimensions left, and you can think of them as one of them is the radius, and the other one is the time. And what happens is that the eigenvalue of the metric in the time-time direction and the space-space direction, so one was negative, one was positive. What happens is at the horizon, the positive one goes negative and the negative one goes positive simultaneously. So space and time effectively sort of switch roles. And that's what happens. And indeed, I think the reason people missed this, though, with hindsight, Einstein did not miss it, as it turns out. It's in his paper. But the reason people missed it starting in the 60s is that they treated the space-time metric as sacrosanct. It had to be a 4x4 matrix, which is symmetric and invertible. And that fails. Now, actually, you see, you could say, why does the space-time metric have to have an inverse? I mean, it's something we normally use in the mathematics of GR. But I realized, and it's only last week, that actually one sort of derivation of general relativity from, let's say, quantum field theory principles is that all you assume is a spin 2 particle. Okay, and actually this derivation goes back to Feynman. Feynman said, people are making all this fuss about curved geometry, but actually, if we have a spin 2 particle, it travels along and it's spinning around with double the spin of a photon, and we have energy and momentum conservation and relativity, and then we try to see what is the most general possible interaction between these spin 2 particles. You can go through various calculations and you discover basically general relativity is the only game in town. That although Einstein had this amazing picture which gave the full nonlinear theory out of geometry, general relativity is all about geometry. Feynman said, actually, this is completely compatible with particle physics as long as we have spin 2 particles. And we would end up with a similar conclusion to Einstein, but on a sort of much more nuts and bolts point of view. Now, from that Feynman point of view, it turns out that to derive general relativity from spin 2 and relativity, special relativity, what you use, and this is a little bit technical, I'm sorry, but what you use in the action is what's called the densitized inverse metric, not the inverse metric. Okay, what does that mean? Basically, you have root minus g. You might remember from the volume element gets multiplied by the inverse metric. And that's the only thing which occurs in the derivation. And it turns out that quantity is not singular in our description of GR.
Okay.
So,
interesting.
It's as well as the freedom to change coordinates, you have freedom to change the variables which depend on those coordinates. So in E&M, we have electric fields and magnetic fields, and we also have the space-time coordinates. And we never think of any particular choice of those coordinates as being better than any other choice. You're free to change variables if you want to make the equation, if you discover the equations are not well-defined or have a singularity, what you should do is change coordinates, either on space-time or on your field variables, to try to make the equations make sense. And if you can do that, that's perfectly fine. So what we are claiming is that there is a choice of variables on space-time, at least as far as the metric is concerned, which leaves everything regular. I believe what happens is that there's something else in gravity called the Christoffel symbol. And the Christoffel symbol actually is singular. And that tells you that as a particle hits the horizon, it experiences a sudden force. And the sudden force forces it to travel up the horizon. In other words, forces it to go at the speed of light. Because the only way to escape falling into the black hole is to travel at the speed of light, because the horizon is a light-like surface. So, and the only way you're going to travel at the speed of light is if you encounter this antiparticle with whom you annihilate. So there is a singularity, but it is not as simple as just saying, "Ooh, the metric is no good on the horizon." That's too simplistic, because the metric itself is not the inverse metric, I should say, is not our metric is actually fine. It's the inverse metric which doesn't exist.
I see.
But there's nothing sort of sacrosanct about the inverse metric. It's just...
Now, if you don't have the inverse metric, can you even form the Ricci scalar?
Yes. So the way you do it is you define the Christoffel symbol and this densitized inverse metric as your two independent dynamical variables. And all of GR can be formulated purely in terms of those. So this was done by Stanley DESE a long time ago, maybe in the 70s. And what he did is he found a sort of much simpler version of Feynman's argument and more rigorous version of Feynman's argument that spin 2 and special relativity give you gravity, give you general relativity.
Now, how would you say that this metric, the eigenvalue swapping at the horizon, how does it affect the quantized field propagation across the surface?
Great question. We are just beginning to study this. What we can say is that in cosmology, when you study the Dirac equation across the Big Bang, there is no singularity at all. The Dirac equation is completely insensitive to the shrinking away of the metric. That's called conformal invariance. There's a mathematical reason why neither Dirac equation nor the Maxwell equation sees the Big Bang singularity, although the metric disappears there. In the Big Bang, it's even worse. All 4 eigenvalues of the canonical metric vanish for a moment at the Big Bang in our cosmological version of CPT symmetric cosmology. So, but it turns out that equations that physics is built from, like the Dirac equation and the Maxwell equations, do not see that singularity. The equations are still perfectly sensible.
Now, why is it that you say that you get annihilated at the surface instead of redirected to some second exterior universe?
Well, because you have to take a particle, which we're assuming is a massive particle, falling into the horizon, and you've got to suddenly accelerate it to the speed of light. Okay?
Mm-hmm.
So that, as I said, the Christoffel symbols do that. They do seem to diverge as you hit the event horizon. But maybe that happens on its own. Maybe it happens as a consequence of meeting your antiparticle. I think, further study is needed. As I say, it's a quantum process. You can only really describe it using quantum fields on this space-time. And that study has only just begun.
Would you then say that the space-time is geodesically complete for causal geodesics that are not radial?
Yes, only if it is possible for a particle with a mass to be accelerated to the speed of light as it hits this surface. That's what makes it possible for the space-time to be geodesically complete.
Mm-hmm.
So it's a big if. Classically, classically, it's very difficult to accelerate a particle to the speed of light. There would be, I don't know, even if the Christoffel symbols diverge, you would say there'd be huge back reaction and all kinds of complications. But the way to study it, we know the process must be quantum. And the way to study it is to study quantum fields in this background. And there are already suggestions from earlier studies of quantum fields on black hole backgrounds that do indicate this kind of behavior is possible. You see, when you study, it's a funny fact about the conventional description of black holes is, as I've mentioned, there are 2 sides. There are 2 exteriors of a black hole. Now, Werner Israel described this using quantum field theory. And what he was able to do is show that you can give a complete description of the quantum field on the black hole by only referring to the 2 exteriors. It's like our picture. You never mention the interiors. You say, look, there's a quantum field and it has some dynamics on the other side and some dynamics on this side.
Mm-hmm.
And then what he showed is that because I can't observe the vacuum on the other side, all I can do is observe one side of this space-time. The consequence of that is that I would see a temperature of the black hole. So he showed he basically argued that the origin of this black hole entropy, which Hawking discovered, is that you are summing over all all the degrees of freedom which you're unable to observe, the degrees of freedom on the other side.
Interesting. When was this analysis done?
That would have been in the 70s. So following Hawking's papers on black hole evaporation, Israel gave this kind of interpretation of what does that entropy mean, and where does the temperature come from? Why is a black hole hot? And the argument is the black hole is hot because you are not seeing, you're only seeing half the space-time. Okay, so so that work also is encouraging for us because it's saying that it does look like it's completely consistent to build a quantum field theory which only operates on the exteriors of the black hole.
So are there any local energy conditions that are violated in the black mirror solution at the surface?
No. As far as we can tell, no. I mean, I should say we've not studied this in enough detail, but no. I think what we've done already shows that there's nothing dramatic happening in the local, in the local stress energy before you hit this special surface. When you hit it, as I say, we expect a signal of particle-antiparticle annihilation.
I assume you're going to say that this is a work in progress, but how do you imagine the specific CPT identification point, the sigma equals 0,
right?
How does it get determined during something that's dynamic or non-spherical collapse?
It's a great question, so the only answer we have is that you have to impose boundary conditions in the future and in the past, and you have to think of the problem quantum mechanically. You have to what is usually called a path integral. So, what is a classical solution of any theory, actually? And the way we understand what classical dynamics is that it is a saddle point, it is a stationary point of a quantum mechanical path integral. Basically, you sum over all paths, and some of them interfere constructively. And the ones which do, when they interfere constructively, that is called a classical path. But the way quantum mechanics works is let's say, the way in which quantum mechanics leads to classical behavior inherently involves data on the past and the future.
How so?
Certainly for gravity, because in the case of gravity, the only, I think, sensible proposed framework for connecting quantum mechanics and gravity is the path integral framework, where you say that I specify, let's say, the geometry, 3 geometry and the matter content at one time, and I specify it at a later time. Okay, I don't tell you the time, I just specify these 3 geometries, and then your job is to find the classical solution which connects these two. And that is how classical GR emerges from the path integral for gravity. This was a picture developed by John Wheeler in the 60s, who was Feynman's PhD advisor. And it's an incredibly beautiful picture. It's very technically challenging, but as far as I am aware, it is the only sort of reasonably well motivated framework for quantum gravity that makes any sense. String theory, for all its successes, never really tells you how a space-time is governed by boundary conditions. I mean, string theory, you always just assume a space-time, and then you scatter strings in it. And so string theory doesn't really give an answer to this question, but Wheeler did in the 60s. And then his picture was developed by Claudio Teitelbaum in the 80s in some magnificent papers, which were largely overlooked, unfortunately, because people got very enamored with string theory. But those papers, I think, are the firmest foundation we have currently for connecting gravity to quantum theory. And as I say, with the path integral, what I do is I specify an initial state, I specify a final state, and then I calculate the amplitude to go from one to the other by summing over all possible paths with interference, with quantum mechanical interference. And so that framework fits, our sort of CPT proposal fits perfectly within that framework. But it's a bit more difficult than classical GR, where you simply evolve the field equations forward, and it's not quantum at all, but you just take Einstein's field equations and evolve them forward in time. And that's fine. That's a classical picture, but it will never make sense of sort of truly quantum phenomena like the ones we expect in our picture to happen on the horizon.
So does that mean the universe is superposed?
Yes.
Does it make sense for the universe to be entangled with itself?
Yes. It has to be. Yes. I mean, I think quantum mechanics, all proposed resolutions of black holes, maybe that's not quite true. There are probably some proposals which are purely classical, but I think anybody who thinks,
I know local structure can get entangled, but global structure?
Yes, absolutely. Yes. Yes, I think, okay, so I'm now going to appeal to observation. Okay. We look at the universe, right? And let's say we look at opposite points on the sky. And those opposite points have never communicated with each other, obviously, because the light from both of them is only reaching us now. So they never had a chance to communicate. And yet they're at exactly the same temperature. Okay? How amazing is that? Now, one explanation for this fact that the universe is astonishingly
uniform
in all directions, right? Homogeneous and isotropic. The one explanation for that is there was a period of inflation in which the universe was actually a very small object in which everything was communicating. So it somehow thermalized. And then it was blown up into this gargantuan universe we see around us today. And they correlated because once upon a time they knew about each other. And they did communicate with each other before the Big Bang, if you like. During the inflating epoch, they did communicate with each other. Now, as you know, I'm not a believer in that picture. That's a very classical picture, actually. And it's extremely ad hoc because you postulate a form of matter, an initial condition, which is this kind of exponential expansion before the Big Bang, in order to explain what we see. I don't think that's necessary at all. You see, I think the error that's being made is the classic one, which is that correlation does not imply causation. Right? We see the temperatures correlated on two sides of the sky. It doesn't mean that one side caused the other one. It just means they're correlated.
So they want to preserve locality, and that's why they came up with inflation? Just a moment. Don't go anywhere. Hey, I see you inching away. Don't be like the economy. Instead, read The Economist. I thought all The Economist was something that CEOs read to stay up to date on world trends. And that's true, but that's not only true. What I found more than useful for myself personally is their coverage of math, physics, philosophy, and AI, especially how something is perceived by other countries and how it may impact markets. For instance, The Economist had an interview with some of the people behind DeepSeek the week DeepSeek was launched. No one else had that. Another example is The Economist has this fantastic article on the recent dark energy data, which surpasses even Scientific American's coverage, in my opinion. They also have the chart of everything. It's like the chart version of this channel. It's something which is a pleasure to scroll through and learn from. Links to all of these will be in the description, of course. Now, The Economist's commitment to rigorous journalism means that you get a clear picture of the world's most significant developments. I am personally interested in the more scientific ones, like this one on extending life via mitochondrial transplants, which creates actually a new field of medicine, something that would make Michael Levin proud. The Economist also covers culture, finance and economics, business, international affairs, Britain, Europe, the Middle East, Africa, China, Asia, the Americas, and of course, the USA. Whether it's the latest in scientific innovation or the shifting landscape of global politics, The Economist provides comprehensive coverage, and it goes far beyond just headlines. Look, if you're passionate about expanding your knowledge and gaining a new understanding, a deeper one, of the forces that shape our world, then I highly recommend subscribing to The Economist. I subscribe to them, and it's an investment into your intellectual growth. It's one that you won't regret. As a listener of this podcast, you'll get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/toe, TOE, to get started. Thanks for tuning in, and now let's get back to the exploration of the mysteries of our universe. Again, that's economist.com/toe. So they want to preserve locality, and that's why they came up with inflation?
Yes. They want to preserve, well, I would say they were stuck on classicality and a classical notion of causality, right, which quantum mechanics violates. They were stuck on that,
right,
and they wanted to preserve locality. So let me phrase the question another way, because there's a sort of very basic way of seeing this. Imagine we're doing statistical mechanics. We're trying to describe the behavior and of gas in a room. So it's a perfectly rectangular room, no doors or windows. We throw a bunch of molecules into it. There's a certain number of molecules, and they have a certain total energy, kinetic energy. They're just flying around and bouncing off the walls. So the question is, what's a typical state, right, for molecules of gas in a box or a room? And many people would say, oh, you need ergodicity. You need the dynamics. What happens is these particles, even if you put them all in a corner, they will spread themselves out so that the typical state will be quite uniform, homogeneous and isotropic, just like the universe. But that takes time, and it requires them to explore essentially all the possible configurations to find the most probable ones. Okay. This argument, I believe, is absolutely wrong, okay, in principle. If you give me a box full of molecules with certain total energy, what you need to do, what you can do, if somebody says, what's the typical state of the molecules in the box? You know the energy, you know the number of molecules. What do? Well, you want to count the states. You want to count all the possible states. So what do? You quantize the molecules. A quantized particle in a box has a certain number of states. And if they're n particles, I know exactly what all the states are. I find those states which are consistent with the given total energy, and they basically live on a shell in the space of quantum numbers, and I pick one at random. Okay. That's a typical state. You can't get a better defined notion of typicality than that. That is 100% kosher, because I quantized everything, so everything's specified by integers. I'm not biasing the calculation in any way. I'm only telling you the macroscopic variables, the energy and the number of particles, and you pick at random. And what you'll find is the typical state is homogeneous and isotropic. That's the explanation. You don't need ergodicity or dynamics to explain correlations. Correlations are inevitable when you have a well-defined probability ensemble. So the same for the universe. Are we really surprised that one side of the universe is the same temperature as the other if we know the dynamics, and if we can show that when we count states, the typical state has the two sides at the same temperature?
Right.
Now, Latham Boyle and I, have published papers showing exactly that we assume Einstein's theory of gravity, the path integral for gravity, and then we generalized Hawking's calculation of the entropy of a black hole using exact solutions in cosmology.
By the way, you should know that I spoke to Latham Boyle here The link is on screen and in the description. It was a presentation on the math of the CPT symmetric universe.
And we discovered that the maximum entropy configuration for a cosmology is homogeneous, isotropic, spatially flat, which our universe appears to be, and has a small positive cosmological constant. It fits with all the observations. So you don't need anything else. You just need to count. You don't need a sort of ad hoc dynamics, which inflationary theorists would have you believe in a prior epoch prior to the standard. But you don't need any of that. You just need the known laws of physics. And indeed, our whole point is, in all our work on cosmology and black holes, that the laws we already know, quantum mechanics, general relativity, and the standard model of particle physics, are capable of explaining everything we see. Okay? We don't need to keep inventing new particles, new dimensions, multiverses. I think the whole field sort of went haywire. And the spirit of our work is to return to simplicity and foundational principles. And again, we've discovered that certain things have been overlooked, which, to us anyway, appear to be much simpler explanations for, everything we see. So I hope, we can't be sure our ideas are right. I mean, they seem to be converging with the data.
Mm-hmm.
One prediction we made is that the lightest neutrino is massless. And just a few weeks ago, the DESE Galaxy survey has now put very tight upper limits on the mass of the lightest neutrino, and it's consistent with exactly what we predicted. And that was a consequence of our explanation of the dark matter. So, it takes us a bit further afield, but basically we are finding that it is possible to explain all observed phenomena in the universe using these basic principles of CPT symmetry and the standard model, and very little else.
Mm-hmm. Okay, let's talk about some cosmological data. So,
Sure.
While we're on this subject, so DESE, a few months ago, I believe they indicated that dark energy can be dynamical.
Good. Yeah, this was the same series of papers. It was just last month. This is the subject of a bet I have with a colleague of mine here. So what DESE has done, it's absolutely fantastic survey of galaxies and galaxy redshifts, and they have tried to infer the expansion history of the universe, how rapidly it was expanding as we look back in time.
And just as an aside,
Sure.
For those who want to know more about your Big Bang is a mirror theory and your whole theory of everything, in a sense, you and I, Neil, had a conversation that went quite in depth, and it also went viral. And if people want to learn more about the recent DESE results, I'll put a link to an Economist article on screen where they explained it as well, but you're about to explain it, so please.
Super. Yeah, so the DESE result, and there have been a number of results along these lines, is what's pointing to a tension. People usually refer it to as a tension between the, let's say, standard model of cosmology, which is very minimal and very predictive, and the data. So one of these tensions is called the Hubble tension, that the most basic parameter in cosmology, the expansion rate of the universe, is called the Hubble constant, and different ways of measuring it give slightly different results. Not hugely different. They differ by about 10%. But nevertheless, this seems to be inconsistent with their estimated error bars. So the Hubble tension has existed for a while. It continues to exist. The new DESE measurements have not shed any light on that. But the DESE experiment discovered another tension, which is that in the standard model, the cosmological constant is inserted as a free parameter. And this cosmological constant is a sort of very, very old theoretical construct. It was invented by Einstein, I think, in 1917, when he wrote down his first model for the universe. The reason he invented it was it is the simplest conceivable form of matter. A cosmological constant is absolutely smooth in space, absolutely unchanging in time. And it's also what we call Lorentz invariant. Namely, if you move through space, this cosmological constant won't change at all. So it's a strange form of energy, which you can think of as just sort of almost like an ether. It's just a uniform, invariant, unchanging thing. And Einstein realized that this type of energy or matter would be gravitationally repulsive, that it pushes space to expand. Whereas other forms of matter, like the stuff we're made of, or dark matter, or radiation, causes space to contract. And so Einstein balanced the cosmological constant's repulsion against the attraction of ordinary matter to make a static universe. So to him, he didn't know about the expansion of the universe. So he thought he had to explain, why is the universe, able to exist when gravity is trying to cause it to collapse? So he used the repulsive gravity of the cosmological constant to hold up the universe. Sadly, he didn't realize that this balance was unstable. And so even in this delicately balanced universe, either you would collapse one way or you would expand to infinity. And so his solution didn't really work. Nevertheless, we have recently discovered, this was in the 90s, that this cosmological constant is about 70% of all the energy in the universe. It's been called the biggest problem in physics. Why is space, why does even empty space have this energy, the cosmological constant, which, as I say, is unchanging and absolutely uniform? Where did it come from? Why is there a cosmological constant? So the standard model includes this. And because it's included, it's able to fit a huge range of data. So it's one parameter, but it explains, hundreds of thousands of observations. So it's a pretty good model. Now, DESE comes along and they said, our data doesn't quite fit the standard model. In the standard model, this cosmological constant is causing a universe to accelerate its expansion, but they find that the acceleration is not exactly as predicted by a cosmological constant. It takes a very weird form. So it was accelerating more in the past, and then apparently in recent epochs, that additional acceleration is going away. Okay, so it's not a model anybody dreamed up. It's not a theory anybody dreamed up. They're finding their data fits, and all they do is a fit. They don't have a theory. So they do a fit to it, and they find that they can fit it by assuming that the cosmological constant, which is one number, is replaced by two numbers, one of which is the value now of the cosmological constant, and the other, if you like, is the sort of rate of change in the past as we look to the past of this cosmos. So they've got a two-parameter model, and they say it fits better.
So what's the bet?
The bet is the following. My colleague said he was sufficiently convinced by the data that he's willing to bet £1,000 that it's correct. However, I looked at the data. Now, the only way, their significance of their data is less than 4 standard deviations. It's not very significant. And they only get the 4 standard deviations, by using 3 different experiments, one of which is theirs, and the other 2 are not theirs. And these different experiments have different systematic errors. So if you combine 3 experiments with their own systematic errors, which are really difficult, these measurements are very, very difficult in astronomy, and you end up with something around 4 standard deviations, it's not very impressive. And particle physics has learned never to believe a result which isn't 5 standard deviations from a single experiment. They're using 3 experiments. So anyway, I'm not convinced. So I said to him, look, what you're doing is proposing a fit. It's not a theory. You've got a 2-parameter fit, and you're saying this is better than a cosmological constant. You agree that this fit is compatible with, let's say, 1,000 theories. You don't even have a theory, right? As far as I know, there's not even one theoretical model. I'm sure people will come up with them, but as far as I know, currently there's not even one semi-plausible.
Quintessence?
No, it does the wrong thing. You see, so that's what I said, because in this fit, the lambda is bigger in the past than now. Quintessence goes the other way. So in quintessence, the field sort of rolling stops. And so the cosmological constant kind of settles, and you stick with it. In this fit, the cosmological constant was sort of big, I don't know, redshifts 3, 4, and then switched off today. It's a very puzzling behavior.
I get the idea. You're not a fan of this. You don't buy it.
No. So I said there's 1,000 models that would fit your data, and there's one model that fits one standard model. So I'll bet you £1 on against your £1,000.
And he's willing to take that.
No, he hasn't accepted that, but he should.
Well, it depends on how certain he is.
Well, he's not willing to bet £1,000 against one.
If he's 1 to 1,000.
Right. So I would say the cosmological constant is a really well-motivated theoretical construct. And it fits pretty well, okay? He's saying an ad hoc 2-parameter fit fits better. I'm not impressed. But he may well. Maybe it's right. I have the utmost respect for the observations. They are going to improve. And if it reaches more than 5 or 6 or 10 sigma, I will have to accept it. So that's great. This controversy is very good for the field.
Just speaking of bets and certainty, I was speaking with Neil deGrasse Tyson, and he said about how there's UAPs in the sky, and are they aliens, are they UFOs? And he thinks it's a 1 in 100 billion chance that they're aliens. So I said, okay, if that's the case, I will put up $1,000 and you put up $1 million, and that should be vastly in your favor.
Yes.
And then he's like, no. I'll put up $100 to $10 or something like that. I'm like, well, then that's expressing you're not as certain as you claimed.
Right. I did this myself, actually. I was a volunteer teacher in Lesotho in Southern Africa before going to university. And I had a little motorbike. Now, all the villagers used to tell me that there is magic. There were, there were witches and people who did things at night. And there's something called a tokoloshi, which is a magical person you make out of various herbs and things, and it will go and kill somebody you want it to kill. So they told me all these stories, which they genuinely believed. And in fact, even the nuns in the convent believed it as well. And so I said, okay, I have this motorbike. You show me one piece of real evidence for magic, and you've got my motorbike. Okay?
Yes, exactly. So you were willing to put your money where your mouth is.
Absolutely. I'm always willing to do that. Frankly, with this bet on the DESE result, if pressed, I would put £1,000 against it. I think there is too much wishful thinking. It's very tempting as an experimentalist to believe that you've discovered something fundamental and shocking. And that's a bias which is very, very difficult to, and again, I'm not holding anything against these particular experimentalists, but I think that is a bias which, they would love. as I pressed him, in fact, this is what he said. He said, look, we better hope this is real, because if all there is a cosmological constant, then the field is dead, meaning that there's kind of no point in doing any more observations because the answer is so simple, because you've solved it.
Uh-huh.
But I have the opposite point of view, that if the observations turn out to be simple, it is putting right in our face that we don't understand. We don't understand the Big Bang singularity. We don't understand this mysterious future of the universe dominated by cosmological constant or dark energy, whatever you want to call it. We don't understand the arrow of time. These foundational questions about the world. There's plenty to do. We don't need a glitch in an experiment, to tell us that we don't understand what's going on. It's obvious we don't understand.
Yes.
So I take the opposite point of view. If these experiments home in on an extremely simple model, that's our best hope. That's our best hope, because if things are simple, then they may be comprehensible. Einstein discovered general relativity on the basis of experiments done over the previous 300 years, which showed that objects of different composition and masses fell at the same rate under gravity. And he suddenly realized, this implies that they're all moving in the same arena, because they're all falling in exactly the same way. So maybe there's something like a curved space-time, which causes them to move through it, independent of what they're made of. And that was his basic clue, which led him to general relativity. So I think the simpler things get from the point of view of observations, the better it is for our eventual understanding.
Okay.
So, this is a purely emotional point of view. I'm not saying one is right or wrong, but my point of view is that the simpler the observations are, the more likely it is that we're going to understand all of them.
While we're here on the cosmos, there's this recent data from the JADES experiment or survey about the spinning galaxies.
Okay, I haven't seen that. Is it a correlation of spins?
Yeah, it turns out that 2/3 of galaxies early on rotate in the same direction.
Okay.
And it should be 50-50.
I haven't studied it myself, but I will be very skeptical. People have looked at the alignments of galaxies, and many, many times, strange alignments have been noticed without an explanation. And almost invariably in the past, these alignments have been found to be just a sort of statistical bias or some other mundane explanation. I think the evidence for statistical isotropy on the sky is huge. I mean, and the best evidence is the cosmic microwave background, that it's just the same in all directions, to basically 1 part in the temperature, 1 part in 100,000. And so it's and that's the most distant structure we know. And it's telling us that we're just surrounded by this almost absolutely uniform sea of radiation. So it's really hard to imagine why there would be big local structures. People do make claims like this from time to time. In general, they have not held up. They're always interesting, because there's always a chance one of them will turn out to be right. But yeah, the track record is not good.
Okay, let's get back to your black hole model.
Okay.
People are probably wondering, what is the physical status of this exterior universe? In the philosophical terms, what is the ontological status of it?
Of the other one?
Yeah.
I mean, we live in one exterior, and there's another exterior. The way we describe it is as a mirror. It's like a mirror. So when you look into a mirror, what you're seeing is the light which came off your face, bounced off the mirror, back into your eye. There's clearly only one side of the mirror, and you don't know anything what's behind the mirror. There is another mathematical description of a mirror called the method of images, in which you take yourself and your face and you make a mirror image of it, where left becomes right, and you put that at the same distance from the mirror as you are, and you throw the mirror away, and that's what you see. So that's called a method of images because mathematically what you do is take your own image, transform it, put it at a certain distance behind the mirror, and it tells you exactly what you'll see. So we believe that this two-sided cosmos is a way of implementing a certain boundary condition at the Big Bang, which uses the method of images. So the image is merely a mathematical device to render your calculation consistent with CPT symmetry. And it ends up imposing a certain boundary condition at the Big Bang, which is therefore compatible with the laws of physics. The same thing for a black hole. We don't actually think of the mirror image universe as a real independent universe at all. It is an image of us, but it is allowed, you see, because the whole construction is quantum, this path integral construction is quantum, fluctuations are allowed on both sides, which are not necessarily mirror images of each other. If you think about the creation of a particle-antiparticle pair, the Stuckelberg picture, the particle and its antiparticle are mirror images of each other, but they're not identical. They satisfy the same they can satisfy the same boundary condition at future time infinity, but the curve can fluctuate differently on the two sides. So we see it in this way. The two sides would be highly entangled. If you try to describe it classically, you will find they are exact mirror images of each other. But if you describe it quantum mechanically, they are not. That's our best guess. I would say it's still an open question how to sort of fully specify this CPT symmetric construction. I don't think we've done it. It's something we're working very actively on. And all the clues we're getting from cosmology and from black holes and from mathematics are helping us kind of build a more precise picture. It's not very precise yet.
I want to end on a couple questions about
Sure.
the black hole. But first, I realized that from our previous conversation about the 36 fields, the scalar fields.
Oh, yes.
You mentioned that people hear that and then they're like, okay, so this is an extremely simple model, minimal assumptions.
Yes.
We're just adding 36 extra scalar fields that weren't there before, and they need to be fine-tuned or tweaked.
Right.
Okay, so help the audience understand why that is not an arbitrary imposition. Like, how is that more simple?
Well, the motivation for those fields are, you're absolutely right to pull me up on this because we're assuming the standard model. And then we're bringing in these 36 additional weird scalar fields for which there is, and I emphasize, no direct experimental evidence yet. Now, let me phrase it the following way. So we were led to these fields by a real observation, okay, which is the fluctuations in the temperature in the sky. I said the temperature is the same to 1 part in 100,000, but it does fluctuate at a level of 1 part in 100,000, and there's a particular pattern in those fluctuations. Extremely simple pattern, specified by two numbers. One is an amplitude, and the other is called a tilt, spectral tilt, a very small number. And those two numbers specify the pattern we see on the sky. So if you ask yourself the question, what kind of field produces that pattern, then the answer is exactly the kind of field we've postulated, this dimension zero field. And in fact, in subsequent work, we have explained quantitatively the fluctuations seen on the sky in terms of that field. Now, we wouldn't believe in those fields except for another theoretical piece of evidence. The evidence is the following. You see, when the Big Bang shrinks away, if you follow the universe back in time, the universe shrinks away at the Big Bang. Now, in order for our mathematical description, this analytic continuation through the Big Bang, in order for that to work, we need the theory to have this very special symmetry at the Big Bang. It's called conformal symmetry. It means that the size can change, but the material contents of the universe do not care. So the radiation, the particles are insensitive to the fact that the size is shrinking away and reappearing. They actually don't see that. Conformal theories only care about angles, not sizes. And the standard model is conformal in the first approximation. And so what we discovered, and this was actually amazing, is that if we have precisely 36 of these rather funny fields, which have 4 time derivatives, not 2, so they sort of violate one of the basic assumptions in the laws of physics for a long time, these fields would cancel all of those violations, and they would cancel the vacuum energy. The standard model has infinite vacuum energy. The 0-point fluctuations in electromagnetic fields, in the Dirac fields, and all the other fields add up in the standard model to a non-zero number. And what basically this means is that you can't consistently couple gravity to the standard model because you've got this infinite vacuum energy. So it turns out that these precisely 36 of these fields cancel the vacuum energy and all the violations of this conformal symmetry. So they allow you to describe the Big Bang. And then in subsequent work, we showed that with this cancellation, when you ask, what is the predicted pattern of temperature fluctuations on the sky, you get exactly the right number. Now, still, you should be worried. These 36 fields, surely I have loads of free parameters, but that's not true. This theory is very, very highly constrained. And in fact, recently we realized that with precisely 36 of these fields, we have an indication that the standard model formulated this way will satisfy what's called maximal supersymmetry. Okay, so supersymmetry is a hypothetical symmetry that relates bosons to fermions. And in supersymmetry, theories that are supersymmetric, the vacuum energy always cancels because you have the same number of fermions and bosons, and one has positive vacuum energy and the other has negative. So we didn't realize at the time that we were looking at a particular case of supersymmetry. But there's something more. It turns out that in 4 dimensions, the biggest supersymmetry you can have is called n equals 4. And in that symmetry, for one gauge boson, and the standard model has 12, but for every one gauge boson, you must have 4 what are called Weyl fermions. That's, let's say, a left-handed fermion. You must have 4 of them, and you must have 6 bosonic fields. Okay, normal bosons. These are 2 derivative bosons. So you end up with this ratio 1:4:6, comes out of supersymmetry. And that's the most beautiful supersymmetric field theory known. It has no divergences. All right, so all the infinities go away. And it turns out, we hadn't realized this, but the counting in our theory is exactly the same because we have 12 gauge bosons. We have 48 fermions in 3 generations in the standard model. So that's the factor of 4. And then we have 36 of these fields, and whereas we should have 6 times 12, 72. But each of our dimension zero scalars actually has twice the number of degrees of freedom of an ordinary scalar because it has 4 derivatives instead of 2. So in fact, we end up with 72 scalars. So amazingly, in our framework, we are finding this signal of supersymmetry. And if that's true, it's going to tell us that we have no infinities in this theory at all as a quantum field. So that's very exciting. It's brand new. We haven't written any papers about it. But the other thing, which is, you see, in our framework, we are not allowed to have the Higgs boson. Okay. The reason is that this cancellation of the vacuum energy and the conformal, what are called anomalies, the violations of conformal symmetry, that cancellation, which kind of happens through a almost miraculous numerology in the standard model, that cancellation does not allow an ordinary scalar field. It does not allow any two-derivative ordinary scalar fields. So the big mystery in our framework is, where did the Higgs boson come from? How was it formed? And it's particularly embarrassing for me because I hold a Higgs chair at Edinburgh, and I'm arguing there cannot be a Higgs boson. Okay. It's inconsistent with conformal symmetry. So
you mean there can't be a fundamental Higgs boson?
Exactly.
But it can be composite?
Exactly. So the only way out is that the Higgs boson is a composite of these 36 dimension zero scalars. Now, actually, that is extremely interesting. And what we are studying now is the quantum field theory of dimension zero scalars. This is getting a little bit technical, but that quantum field theory turns out to be asymptotically free, meaning that at very high energies, the coupling vanishes. It becomes a free theory. That's great because it means that this quantum field theory actually exists mathematically as a well-defined theory, whereas the usual Higgs theory does not. The usual Higgs theory is not asymptotically free. The coupling blows up at large energies. And so that theory, we believe, is sort of ill-defined. If you probe it with a very powerful microscope, you will find it doesn't make any sense at all. It just gets sort of worse and worse. The coupling gets bigger and bigger, and there's no good limit. So the dimension zero scalars have a better limit, and now there's a chance that we will solve what's called the hierarchy problem. The hierarchy problem is that the Planck mass, which is about 10 to the 19 GeV, associated with gravity, huge energy scale, only probable through the Big Bang itself. When we look at observations of what came out of the Big Bang, we can talk about phenomena due to Planck scale physics. But this Planck scale is 10 to the 19 GeV. The other scale we have to put in to the standard model is the weak scale, which is about 100 GeV. That's the mass of the Higgs boson. Those two scales and the cosmological constant are the 3 mass scales in the standard model, which have to be inserted by hand. Okay, so far, because we don't really understand their relationship. But the hierarchy puzzle in particle physics is, why is the Planck scale 10 to the 17 times bigger than the weak scale? Okay, this sounds like incredibly contrived. You don't get 10 to the 17 just by playing with pi's and 16s and so on. Or you might, but it would require a lot of contrivance. Okay, so the hierarchy puzzle was a huge motivation for supersymmetry. Conventional approaches to supersymmetry, that they argued you had to have all these superparticles essentially to cancel quantum corrections that would push the Higgs mass up to the Planck scale. So what we have with the dimension zero scalars is an opportunity to explain this ratio in a much more compelling way. The way you explain it is because in an asymptotically free theory, the coupling constant runs with energy and goes to zero at large energies. So you say, imagine the coupling was about 1/30th at the Planck scale, some moderate number. at the Planck scale. When I run it down, now it only runs logarithmically in energy, which is very, very slow. So let's say it's a 30th at the Planck scale. You can ask, what energy scale does it become 1? And that can be 100 GeV. So you start at 10 to the 19, but where it's a 30th, and it becomes 1 at 100 GeV. There's no fine-tuning in that. You have explained this huge hierarchy without very naturally, because it's only logarithmic. In fact, the same explanation works in QCD. Nobody wonders why the mass of a proton is 1 GeV, whereas the Planck mass is 10 to the 19. And the reason is that QCD is asymptotically free, and the coupling becomes strong at 1 GeV, and that determines the mass of a proton. So with these dimension zero scalars, we have the chance of making the standard model much more compatible with the facts. Now, it's only a chance, and we're busy doing lattice theory computations with dimension zero scalars to see how this Higgs mass would emerge, how it can behave as a Higgs boson. But and if that works, it'll be very exciting, because it will then create a rival to the standard model Higgs, which could be, so the two can be tested against each other at future accelerators.
Mm-hmm.
But again, what we stumbled across is a simpler way of solving the hierarchy puzzle than supersymmetry, which, yes, it involves these weird extra fields, but they don't have any particle excitations. There's no more particles. All these extra fields do is actually change the vacuum. And they change the vacuum in such a way as to make it consistent with this very profound symmetry called conformal symmetry. So potentially here is a rival to the standard model, which will explain the hierarchy and the Higgs mechanism, which broke particle physics symmetries, and also fit the cosmic microwave background. I mean, it's absolutely a unified theory of the whole cosmos, stretching from the tiniest scale to the largest scale, and it may be within our grasp. I mean, it's tremendously exciting. And in fact, it feels to us like it's just around the corner.
So, Professor, there's so many more questions I have for you, and I'll have to save them for next time. But
Okay.
if you can answer briefly about these two questions, because it seems like your theory, which I don't recall if it has a name, a moniker.
CPT symmetric universe. I think that's probably the simplest. Yes.
So the CPT symmetric universe.
Yes.
Does it also solve the measurement problem or the flow of time?
Ooh, these are great questions. The flow of time, I would say yes.
Not the arrow of time, but the flow of time.
Oh, the flow of time. Why does time appear to be flowing? Okay, good question. I would say so far no, but there are real prospects for doing so. Nobody has even tried to calculate whether there would be an apparent flow of time within this framework. It's a reasonably well-defined mathematical framework. And indeed, I think it would be very good to try and do calculations to see whether for macroscopic entities like ourselves, there would be an apparent flow of time. So it possibly will solve that puzzle. What was the other one? The flow of time and
measurement.
No, my colleague Latham Boyle,
who I've spoken to, by the way, and a link will be on screen and in the description just for people who are interested in learning more about this theory and seeing your collaborator. He gave a presentation.
Yes. So Latham has a notion that, in quantum mechanics, things are doubled because we have real numbers and imaginary numbers. And quantum mechanics works with both, whereas classical mechanics only works with real numbers. And so Latham believes and hopes that this doubling of the universe will be in some ways reflective of the fact that to describe it properly, you need both real and complex numbers. which means you have double the number of numbers, if you like. And that is not unreasonable, because what happens in this two-sided universe, you could ask, why are there two sides? Why are there always two sides in black holes and in cosmology? And the reason is a mathematical one, which goes back to work of Hawking long time ago, where Hawking noted that in geometry, the sort of simplest kind of geometry is called Euclidean geometry, in which everything is like space. Whereas Minkowski introduced Lorentzian geometry, where you have one time and three space. Okay, to go from one to the other, you make time imaginary. It's a very old trick. You have in the space-time distance or metric minus delta t squared plus delta x squared, delta vector x squared. Time comes in with a minus sign. That's very, very basic in relativity. But if I make time, if I say t is I times tau, where tau is real and I is the imaginary number, then the metric is plus, 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 four pluses. So Minkowski realized this, actually, that if you make time imaginary, you're dealing with Euclidean geometry. So relativity becomes just Euclidean geometry. So Hawking used this fact. He started with a Schwarzschild black hole, which has one time and three space. He made time imaginary, and he discovered a Euclidean version of the geometry. And turns out that Euclidean geometry is completely non-singular, right? It doesn't have the curvature singularity at all, anywhere. In fact, that Euclidean geometry pretty much describes the exterior only of the black hole. So if I have this picture where imaginary time, so in the complex numbers, you have the imaginary axis and the real axis. And if you describe a solution up the imaginary axis, okay, which is this, as I say, Euclidean geometry, when you come back to the real picture, there are two ways to go. You go left or you go right along the real axis. And those are the two sides of the black hole. And those are the two sides of our universe in cosmology. And so this way of going from real numbers in Euclidean geometry to complex number, use it through complex numbers to Lorentzian geometry, which has a, quote, real time and a direction of time, involves precisely, and which doubles the time directions, that indeed is related to how you go from how you go between complex and classical mechanics. And so I think it's not an unreasonable hope that we will that this doubled picture will tell you something about why quantum mechanics uses complex numbers and hopefully what they mean. So, I mean, there's another factor of two. In quantum mechanics, the probability is the square of the amplitude. And in our doubled universe picture, it's just crying out to somehow say that you double things, you square things. They're two sheets to the universe. So, yes, we are hoping that this picture will shed new insights into the very mathematical structure of quantum mechanics.
Before we get to just your advice to students and your hope for the future of physics, I just have a quick question about the black hole.
Sure.
So, given its horizon structure, does it satisfy certain uniqueness theorems such as no-hair theorems? Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org. Like uniqueness theorems such as no-hair theorems.
Yeah, that's a good question. I would say yes, because those uniqueness theorems only use the Einstein equations, and we are satisfying the Einstein equations. So indeed, I would say they do satisfy the uniqueness theorems. We don't expect black holes with any hair to emerge from this construction. But the question of the dynamics of the black holes as they merge and settle down to those unique stationary states, that's where the difference might be revealed between our picture and the conventional one. So the stationary states we would agree on.
I see.
But in the dynamics, how you get there, we might be different.
If an observer is going tangent to the surface, do you imagine there would be an infinite tidal force to the horizon?
I don't think so. All the indications are, you see, what we find is that in the stationary case, there is no divergence in the curvature on the horizon at all. All the curvature invariants are finite on the horizon. So that's in the stationary case. In the dynamical case, I don't expect it'll be very different, because I think if matter's falling onto the horizon and then annihilating and zooming off up the horizon and being released at infinity, I don't expect that to cause infinite anything. But yeah, we shall see. We haven't done those calculations.
And do you expect the Hawking entropy, the Bekenstein-Hawking entropy, to be recovered from
Yes.
the entanglement during evaporation?
No. So in the usual picture, the entropy of a black hole, people like to explain. I mean, the entropy calculation itself it uses this imaginary time picture. It's very elegant and unique, but it doesn't give you much physical insight. Okay, the way Hawking calculated the entropy. By the way, that way is exactly the same way that Latham and I calculate the entropy of cosmology. It's a very mathematical construction using imaginary time. We literally replicated Hawking's black hole calculation for cosmology, and we were very surprised we could do it at all. And that gave the answer for the entropy of a cosmology. But as I say, it's very mathematical and abstract, and it's quite hard to figure out what it means. So people are still arguing about this for black holes. Now, what is this entropy counting? In some sense, people believe it's the entropy of stuff which fell in, and that we cannot. It's all the states. It counts the number of states of everything that fell in, which we can't see. Okay, so that's how they explain the entropy. But there are big puzzles with that too, you see, because the Hawking's entropy calculation does not depend on the number of particles in the standard model. You know, the standard model has a certain number of particles, a certain number of forces. Those just don't come into the calculation. So according to Hawking's calculation, if I double the number of particles, so I could make, chairs and tables out of standard model fields or different versions of standard model particles.
Yeah.
That, according to Hawking's calculation, that would not change the entropy of a black hole, and that's called the species puzzle. Hawking's calculation is independent of the number of particle species.
Yeah, even if there was less species, like just one.
Yes, if there's only one, it would give the same answer. So I would now. People have trouble explaining this. Okay, there's a very profound puzzle. How can it be that the entropy of a black hole is independent of the number of different types of particle there are in physics? I think the only sensible resolution is that if his calculation's correct, and the answer for the entropy is unique, then combining gravity with particle physics is much more unique than people expected. The mere inclusion of gravity forces the number of particles to be some number. And you just can't consider coupling one particle to gravity. You see, and that's the evidence we're finding in this cancellation of anomalies and vacuum energy, again, that's an indication that you can't just chuck any old particle species into gravity. You have to couple the fact you want a consistent theory, including gravity, tells you how many particle species you can have. So,
sorry, just a moment. Is that formalized yet? Is that a no-go theorem that you all have come up with?
yes, I would say if you want the conformal anomalies to cancel, we can give you the precise conditions, and they heavily constrain how many particle species you can have. So we use this to explain why there are 3 families of particles.
Interesting.
When we cancelled the vacuum energy and the trace anomalies, we explained why there are 3 generations of elementary particles. It is, as far as I know, the simplest explanation anyone has ever given. Yeah, so cancelling the vacuum energy and these conformal symmetry violations predicts that there are 3 generations of elementary particles.
When you postulate the global CPT symmetric boundary conditions, does that comport with the observed baryon asymmetry?
Yes. Yes, that's fine. The reason is that all of this anomaly cancellation requires 48 fermions, which is 3 generations of standard model particles, which have 16 particles each. The 16 includes a right-handed neutrino. And we use one of them to explain the dark matter. Okay, so in fact, this is what started us around this whole journey, is that we found we could explain the dark matter much simpler than anyone else as being one of those right-handed neutrinos. Now, right-handed neutrinos violate lepton number. It's just a fact. If you put them into the standard model, lepton number is no longer a good symmetry. In fact, there are no good symmetries left.
Global, though, correct?
No good global symmetries left in the standard model. And so lepton number, baryon number are all violated. And there is this picture, the simplest picture of how the baryon asymmetry was created is a scenario called leptogenesis. Basically, that these right-handed neutrinos are just created thermally by high-temperature processes in the early universe. And then as the universe expands, these right-handed neutrinos, which are heavy, decay, and those decays violate baryon number.
You mean lepton number?
Oh, sorry. They violate lepton number. And then, so you produce a net lepton number. And then within the standard model, there are these very beautiful processes which happen called B baryon. They're called B plus L violating processes. They go through something called a sphaleron. You may have heard of. It's basically a non-perturbative process, which is now pretty well understood, whereby this lepton asymmetry is converted at the electroweak scale into a baryon asymmetry. So basically, this is quite a long story, which I participated in the, it would be in the 90s. And this is now the simplest explanation of where the baryon asymmetry comes from. Unfortunately, there's only one number to predict, which is the baryon asymmetry. Okay. And in the standard model with right-handed neutrinos, there are more than enough parameters to dial them to fit the observed number. So in a certain sense, it's not terribly predictive. It's just, there are enough parameters that you can fit the observations. So that scenario fits perfectly within our overall picture. I don't think we're adding anything particularly new to it. But that picture, I think, is very compelling. And in fact, there's a new accelerator which will be operating in 2 years' time at Brookhaven, where they are going to be able to explore these sphaleron processes, actually in QCD. But these same non-perturbative processes are going to be explored experimentally, and that will shed light on exactly how they happen in the standard model. There's not much doubt they are there. They have been calculated, but so far there's no direct experimental evidence. But this is definitely an avenue for the future.
Speaking about the future, please tell us your vision of physics in the future, what you hope for physics, and I'm speaking about physics research. And also, if you're speaking right now to physics students, graduate students, PhD students, new upcoming students, prospective students, what is your advice? I was just at the Perimeter Institute, actually, where you were a
Oh,
director
good.
for 11 years or so. And so
That's
it turns
right.
out this podcast is somewhat viral at the Perimeter Institute. I felt like a celebrity there. So
Good.
there are probably many people who are watching from there.
Lovely. No, Perimeter is a wonderful place, and I had the opportunity of a lifetime to go there and be director for 11 years and to try to shape it. So vision for physics. I mean, physics is an absolutely incredible field. We can write down on one line all the laws of nature we know, and the suggestions are, and this is the lines I'm working on, that one line is enough to explain everything in nature, at least at a very elementary level. The universe appears to be incredibly simple on large scales. We've got this standard model, the lambda CDM model, which has only 5 numbers, fits everything. The universe is also very surprisingly simple on small scales. The Large Hadron Collider, most powerful ever microscope, has not found anything beyond the Higgs. So it may well be that the laws of physics we already know are more or less the complete story. And putting together these laws into a coherent framework which explains the arrow of time, the passage of time, the future of the universe, which is strange and vacuous, dominated by this cosmological constant, apparently, into the infinite future, and the Big Bang singularity, even more puzzling, that everything came out of a point in our past. Putting that all together, I think, is an absolutely wonderful intellectual challenge. And so, I couldn't be more excited about physics. Obviously, new data from experiments is very, very important, but if that new data confirms the standard picture, I think that will be a great sign, the minimal picture, let's say. I think that'll be a great sign that we're on the track to understanding these much bigger and deeper questions. And so that's what I'm hoping for. If they contradict it, of course, the picture has to be revised, and potentially the whole picture has to be revised, which you might say is even more exciting. So, so I think physics has has an amazing future ahead. I still cannot get my head around how successful physics is. I mean, it's just bizarre that Einstein, more or less, with a little guidance from experiment, more or less conceptualized, the equations which govern the expansion of the universe, predict black holes, gravitational waves, everything. That's the kind of, amazing unification which thinking about physics can achieve. And to some extent, Higgs did the same with the predicting the Higgs boson in the 1960s. And so that's the kind of unique property of theoretical physics, which I don't think there is in any other field of science, that starting from very coherent, economical, mathematical principles, one is able to explain this kind of bewildering variety of natural phenomena. So that's really exciting. Now, in contrast to physics, you have scientific disciplines like molecular biology or AI or, computation or quantum computing or whatever, which are looking at complexity. And it seems to be a fact about the universe that all the complexity is in the middle. It's on intermediate scales. Nature is very simple on small scales, very simple on large scales, but in the middle where we live, we haven't succeeded in understanding it. We don't really know what life is. We don't know what consciousness is. Those are wonderful challenges too, but it's difficult to be, to predict when we will make advances in understanding complexity. Is it all going to end up as just a big mess of computers with algorithms? I don't know, but that's personally what puts me off working in that field. Is it's too heavily computational, and I don't see the same elegance, economy, and so on. And maybe that's just inevitable. Nature is not very economical at intermediate scales, and that's what allowed us to exist. So yeah, that's how I would put physics. If you like simplicity, if you like powerful predictivity, right, and explanatory power, then nothing beats physics. So it's very compelling from that point of view, and it just feels every day feels a wonder to be involved in a field like that. It's such a privilege. I mean, it's something like, I guess, the Buddhist monks or someone who've reached some very high level of enlightenment must feel the same way. It's just such a privilege to feel you're part of this. Now, advice to young people, I would, based on my own career, my own experience, I would say the time you spend thinking about foundational issues, the most basic questions, what exactly is going on in the formalism? Is there a more simple way of explaining it? Questions you try to understand the interpretation, the meaning of those equations. That time is never wasted, okay? Because that's always the source, I would claim, of the most profound insights. So I see young people today very anxious about the future, very anxious about career in particular. And I think that can be very destructive in terms of making people work on things which are, publishable in the short term, fit within some standard paradigm, so the referees will wave it through. And I think that is disappointing. There's a vast amount of literature coming out on fields which essentially aren't making much of a contribution except in volume. Okay, in volume of material which doesn't particularly have any novel or useful insight. So I would encourage young people to, think, why did you go into this field? If you went into it because of its beauty, economy, simplicity, power, stick to that. Don't give up your principles for the sake of a few quick papers. Of course, you have to be pragmatic, so you do have to find projects which are doable and worth publishing. But the more time you can spend on foundational issues and on really trying to do something novel, which adds to our understanding, the better you will do at physics. I think that quality is quite rare, but Perimeter Institute is one of the few places actually in the world where the culture among the young scientists is of strongly promoting independent thinking rather than just following established schools. And so I think that's one of Perimeter's great strengths, and I just wish there were more places like that around the world.
That was my sense as well. Thank you so much, Professor. It's always a pleasure speaking with you.
No, I think thank you very much for the work you're doing. I think your podcast is pretty unique in bringing together philosophers and thinkers, across the spectrum. It's very unique, and I think it's really commendable. I mean, it's because it's accessible to young people. You're going to encourage them to think, do I want to be a philosopher? Do I want to be a physicist? Do I want to be a mathematician? And I know from my own part, when I went into science, I never thought about any of this. I had no idea. It was just a random walk. I wasn't systematic in my approach to my own career at all. And I think the guidance people can get from online informal conversation is really very valuable. They can say, aha, that's an idea that I would like to learn more about.
Well, if your career is an erotic walk, then it'll certainly be a theory of everything that we'll have to discuss at some point.
That's right. That's right. Okay, thanks very much, Curt.
I've received several messages, emails, and comments from professors saying that they recommend theories of everything to their students, and that's fantastic. If you're a professor or lecturer and there's a particular standout episode that your students can benefit from, please do share. And as always, feel free to contact me. New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gained from rewatching lectures and podcasts. I also read in the comments that, hey, TOE listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Curt Jaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.